Welcome to Topology Lecture 13 on covers. So let's get right into it. Definition. A cover of a set X is a family A of subsets such that X is the union over the family. The cover is finite if it's a finite family. The cover is countable if it's a countable family. And if A and B are covers and A is a subset of B, then that means A is a subcover of B. All right. Manetti makes a comment here in passing that the mapping I maps to I, it's onto for this family, but it's not assumed to be injective. I don't know quite what to do with that, but great. So just keep that in mind, I suppose. I mean, goodness, I don't ever recall working with an index which wasn't by, like a one-to-one kind of thing. I mean, yeah, the index doesn't have to be a natural number, but to use indexing which is not injective seems very strange to me. Goodness, anyway. So, anyway, I am following Manetti, so there's one of the things he said. So a cover of A of a space X is said to be open if every A in the cover is open, if closed if every set in the cover is closed, locally finite, if for every X in X there exists an open set in X that meets sets in the cover for, at most finitely many A. So like, well, he mentions, so his example, I'm going to come back to 3 here in just a second, but any basis of a topology is an open cover, right? Because remember, the union of the basis has to cover the whole set, so that means a basis is an open cover. This is an example of a locally finite closed cover of R. First of all, it's clearly closed because n to n plus 1 closed intervals are closed, right? And if you let n go through all the integers, it's pretty clear that that covers everything, right? Here's kind of a silly picture of it. Let me scooch this up a bit here. So here's a picture of the closed cover of R by these closed sets going from, one integer to the next one in succession. And so let's see here. Can we find an open set containing 1.5 which only meets finitely many A in the cover here? Well, I mean, whatever you like, right? But here I'll do like, oh, I don't know. Here, I'll do this to this, all right? So that'll be my V. I'll put V equal to, let's say, minus 0.4 to, oh, I don't know, 3.6, right? That's definitely an open subset of R. And you notice that V only intersects what? V intersects A. V intersect A is not equal to the empty set for what? Just for A equal to, either we're looking at 0 to 1, or 1 to 2, or 2 to 3, right? And that's it. So there you have it. And you can definitely prove if you have an open set. Well, not any open set, right? There exists an open set, I should say. It's not for any open set, because if it was for any open set, that definitely is not true. I mean, the real numbers altogether are open, and of course that intersects the closed cover here at infinitely many places, infinitely many members. But if I pick any point, I can find an open set around that point, which, I can find an open set around that point which intersects the family, this closed cover here at most finitely many of them. Of course, if I used like a ray that went to infinity or minus infinity, then that wouldn't work, but it doesn't have to hold for all V, right? It just has to be that there is a V that intersects, that meets the cover at finitely many subsets in the cover. So it is locally finite as claimed. All right. Okay, so let's move on here. Page number 2. let A be a cover of X. We call A an identification cover in the case that when U is a subset of X is open, that's true if and only if U intersect A is open for all A in the identification cover. All right. So that's the definition. So an example of something that's not an identification cover would be the singleton cover in the reals with the Euclidean topology, because while it is true that the singleton cover is a cover, if you take U, a real, a subset of the reals, an open set, and you look at the intersection of that open set with like this, a singleton, and that singleton is singleton is the singleton of a point in the set, then the open set intersect with the singleton is just the singleton set again, and the singleton set is closed. It's certainly not open in the Euclidean topology, so this is definitely not a identification cover. So what is? Okay, so proposition, let A be an identification cover of X. I guess we're not really explaining what an identification cover is just yet. I mean, well, there's the definition, right? But what is it? Well, we've got a couple propositions here to gain a better sense of that. Let's get to it then. Let A be an identification cover of X. A map from X to Y is continuous if and only if for any A in the cover, the restriction is continuous. All right. So, so I think the forward implication here is just the fact that if you have a continuous map and you restrict it, to a subset of the domain, then it's a continuous. So the restriction of a continuous map is continuous. The converse direction perhaps is more interesting. Let's look here. So suppose U, a subset of Y, is open, then and we're assuming that F restricted to A is continuous for all A in the identification cover. Well, if we look at the inverse image of U intersect with A, well, that's the same as the intersection of the restriction of F to A inverse image of U, and that, by assumption of continuity of the restriction, is open, right? And noting that A is an identification cover, we can conclude that since this is open for arbitrary A, and remember, being the intersection of a set with the identification cover for arbitrary members of the identification cover being open is tantamount to being open according to the definition of identification cover. Consequently, F inverse of U is open, and if F inverse of U is open, since U is an arbitrary subset of the codomain of F, it follows that F is continuous. So we've proved the converse direction there, right? So therefore F is continuous. Conversely, if F is continuous, then the restriction is continuous. So there's the proof of that proposition. Next up here, let's scooch this up a bit here. All right, so open covers and locally finite closed covers are identification covers. So let me try to see if I can get it all. Let's see here. I think basically it works like that. If I remember how I've written this. So maybe we can just do it like so. Well, anyway, we'll give it a shot. So open covers and locally finite closed covers are identification covers. All right. So suppose A is an open cover, all right, and U is a subset of X. So U intersect A is open for all A and A. Well, if U intersect A is open for all A and A, then U intersect A is open in X as well. All right. Fine. So then U, we could say, is the union. I mean, here, I think this is actually the proof of it. U, which is equal to the union since A is a cover, you can form U by the union of the intersections of the covering sets with U. So, I don't know, what maybe is a picture of that. It's something like, you know, U is something like this, right? And then if you've got all these covering sets, right? And they cover. So if you just take the intersection of U with all these covering sets and you put them all together, right? You're going to get back the whole purple set again, because the cover covers everything. So you can rewrite any set as a union over its intersection with the cover. Ah, markers, behave. Go back to your home. Fine. The new home is my coffee mug. Anyway, so now since each one of these is open, we've got a union of open sets which is open. In other words, the condition that the condition that U intersect any A in the cover is open implies that U is open. All right. So that's like going back to the definition. U open implies that, right? Now the identification cover, we also need this implies that. So I guess we're going to do that next here. Ah, stupid. Ah, sorry. My things are all out of order here. Not really. So it looks like that's maybe the converse direction of that is just obvious. Think about that. If U intersect A is open, we've got an open cover. Yeah, I guess the converse direction is just kind of clear already from what we've said. So let's go on here. The finite closed, so now we're going to assume that we've got a locally finite closed cover. All right. But this proof looks like finite closed, doesn't it? Let me check. Let me just check something here, because whenever I see, sometimes I just copy a word down wrong, and then, you know, it would be silly to make a big deal about it when it's actually just me copying a word wrong. Let's see here. So we're still in covers, which is section 4.3. This is theorem 4.34, open covers, and the locally finite closed covers are identification covers. Okay, it is what it says. Fine. All right, I'm just trying to process, why is he assuming that the cover is finite? It's not immediately obvious to me that locally finite implies finite. All right, anyway, let's try to process this argument and see where it takes us, all right? So X is a union of C1 through Cn, each one of them closed. Take a subset of X such that the intersection with Cj is open in Cj for all j. Right, B is the complement of X by U. And notice that B intersects Cj is the complement of Cj by the union, rather the intersection of U with Cj. And that's going to be closed because it's the complement of something open in Cj. Alright, so then we can write B as a union over the intersections of the B with the cover, C1 through Cn. And each one of these is closed, and we've got a finite union of closed, which is therefore closed. Alright. So I guess this is really a lemma. I think this whole bit right here is essentially a lemma for what follows. Let's see. So if we have a locally finite closed cover, we may select an open cover A such that CI intersect A such that I is an I is a closed finite cover of A for any A in A. So hmm. Well, I guess, okay, so I guess the point is you're using the A, you're picking A here to be the V in the definition of the locally finite cover. And so basically think of the A as being the V. If you keep picking them like that at each point, then you only need finitely many of the CIs at that. You only need finitely many of the CIs to cover V. Right? Okay, fine. Yeah. For any, and you can do that for any A in the open cover because you've constructed the open cover with the local finiteness of the closed cover in mind. Like the construction of this A is based on this in the local finiteness. Therefore, if U intersect CJ is open in CJ for each J, then U intersect CJ intersect A is open in the intersection of A and CJ for all A and A, and U intersect A is open in A for all A and A, thus U is open in X. So there we're going, now we're using the fact that an open cover is an identification cover to finish the proof of the second half of the theorem. So okay, I think that makes sense. But anyway, let's I think that's it for this one. So this was kind of a short lecture. I hope you don't mind. But that concludes what I have to say about covers here. And this again was section. What section were we on here? Section 4.3, page 171 of Manetti here. Anyway, thanks guys.